my student with whom I'm basically learning this whole material and working on this problem. And we thought we had made a significant improvement, but we aren't so sure about it at the moment. So what we will do is we'll present the background materials, we'll tell you what our ideas are, and hopefully something will come up. Okay. So the problem is, as Manoj Gupta had pointed out, we are interested in the fully dynamic framework, and we want to maintain a maximal matching. And we want to maintain a maximal matching without three-length augmenting paths. And the reason for doing this is that there are very good algorithms for maintaining maximal matchings, and we wish to maintain matchings without three-length augmenting paths because that would be a 2/3 approximation to a maximal matching. This matching that we would maintain would be at least 2/3 the maximal matching in the fully dynamic framework. And the hope is that we will achieve square root and amortized update time, and the algorithm will be randomized. And so that's the plan. So we'll, so I'll skip through all this because there was already a nice introduction to this already. So can we do better than just starting from scratch all over again? And so there are many such examples which you have seen. And this is probably looking a little different. So what you have is an update query sequence, and you're interested in basically the sum total running time. That would be the amortized analysis to service these update query sequences. So that's the analysis that we will basically do. And that's the amortized analysis. You could also ask for the worst case time for each of these. Right? So, again, there are multiple frameworks here. We are interested in the fully dynamic framework. And we are interested in the graph algorithms, which is what we've been talking about all along. Alright, so let's just quickly go through what is a maximal matching. Right? So you cannot add one more edge without violating the property that it is a matching. Okay? And so what would be the simplest approach? Right? So basically, these are the vertices, right? And a new edge that's being presented to you. Right? And if u and v are free, then you basically, without much effort, you just add this into your maximum matching. Okay? And this also takes very little effort. And for that matter, for every edge that is presented to you, right? So you just need to ask if both the endpoints are free, right? And this can be done quite easily. Right? And the challenge comes when you have to do a delete. Right? So this was the edge, right? That was there in the matching. Now it's deleted. So now you need to figure out whether there is a way to match both u and v to somebody else. Right? And obviously this can take potentially as much time as the degree of the vertices u and v, and this could be, we have nothing better than an order of n estimate, which is the order of the degree, and we have not used any information about the degree or where we search for the replacement edges, right, which would match u and v once the edge uv is deleted from the match. So what is a very nice result, which part of it we are going to present. So there is a very nice result by Surendra Basmana, Manoj Gupta and Sandeep Sen, right? So where it's a fully dynamic maximal matching in order of log n update time. The first part of this paper, right, is a very nice expected amortized analysis, right? It's a randomized algorithm, right? And the amortized running time is order root n. And it basically maintains a maximum matching. So what I do is I present this algorithm and the analysis. I probably have an analysis which is probably different from the way it's presented in the paper. One could argue that, and I'll use the board to present it. And hopefully that analysis will show how to take this technique towards maintaining matchings without three-length augmenting paths. Alright, so our goal is eventually to maintain matching without three-length augmenting paths. How does one fix a three-length augmenting path? If you discover that this is a three-length augmenting path, there are 2 or 3 vertices at the end, and this is a edge in the matching, and these are 2 edges which are not in the matching, you basically flip them and obviously the size of the matching increases by 1. And if this was a maximal matching, this also continues to be a maximal matching. Right? So this is a useful property. And one another useful property is that after doing this operation, the vertices that have participated in this operation do not participate in other gradient augmenting. So this we will try to use later when I show you how to remove gradient augmenting. Okay. So the motivation for maintaining gradient augmenting paths is this very nice theorem, right? So that if you maintain maximal matchings which don't have 2k plus 1 length augmenting paths, then such a matching would be an 1 plus 1 by the approximation to the maximum granularity matching. This is very easy to actually see. These are what we do. Okay, so now let's just go to the Djs algorithm. The crucial thing in this Djs algorithm is to trade off two kinds of parameters, right? And one parameter is immediately visible to us. Right? The workload that is involved in searching for an edge to introduce into the matching, right, at an unmatched vertex is to see how many neighbors are free. Right? So how many edges incident on it are. You have to inspect the edges incident on it to see if the other endpoint is free. That's one immediately visible workload. Right? And the worst case bounds that you can use in that case are basically the max degree, right, which you can't do anything better than n. So the natural question here is that, look, assuming that the update sequence is fixed, right, can I now, for every edge, the endpoints of the edge under certain conditions, right, only one of them will search, right, whether this edge will participate in a matching or not, right, then one of the endpoints is free. So in other words, can we distribute the degree, right, carefully in such a way that we can trade off two parameters, right, the number of times we do expensive searches to find to replace an edge, right, that has been deleted by something else so that you get a maximum matching. So two parameters. One parameter is the neighborhood search that you will do. The other parameter is the number of times you will do an expensive search. Right? So how does one actually come up with and we will argue that the number of times you will do an expensive search is actually bounded by the number of edges of vertex owns. So this ownership concept is a very interesting thing, and the motivation is that somehow you want one more parameter to play with, right? And you are also going to use randomization. And I just define what this ownership is. So what we do in the algorithm is, as the graph arrives, we arrange the vertices in levels. We just use two levels. A vertex can be at level 0 or at level 1. Right? And I'll tell you the rules for the conditions under which a vertex will stay at level 0 and then it is going to go to level 1. Okay. So when an edge is presented to the algorithm, if both the endpoints are at level 0, then both the vertices are said to own this edge, right? Own this particular edge. On the other hand, if one of the endpoints is at a higher level, it's going to be the vertex at the higher level that is going to own this vertex. Okay? So in some sense, this is a snapshot of the algorithm. Right? So vertices will be in two layers. The edges which are being presented will be owned either by both the endpoints, if both the endpoints are at level 0. If one of the endpoints is at level 1, that vertex is going to own this. Right? And what does ownership basically mean? Ownership basically means that every vertex will try to search its ownership list for a partner to get matched. Okay. Now, it's the size of the ownership list that will decide whether a vertex stays in level 0 or at level 1. Okay. And as I go through it, I'll give you the calculation for why the size of ownership list is going to be root n. Right? So basically, what we will observe now, and I'll try to motivate this parameter root n, if the ownership list becomes greater than or equal to root n, then that vertex will go up to level 1, okay? And somehow this gives us an advantage. Okay? I'll tell you what the advantage is in the presence of randomness. And if the ownership list is small, which means it is smaller than root n, then the vertex, and if it is free, that vertex will surely stay, right, at level 0. Unmatched vertices, right, will stay at level 0, right, and their ownership list will be small. If the ownership list becomes large, then it will go to the next level, to level 1, and we will see how to ensure that it gets matched, and here we will use randomness. Yeah, so if both the endpoints are at level 1, then only one of them owns it, right? So this is crucial. Okay. So to argue that we maintain a maximal matching, right, the Djs algorithm maintains certain invariants, most of which I have just listed. The one that I have listed just now are that we always ensure that for 2 I have listed, right, so endpoints of the match stage are always at the same level. And every vertex at level 1 is matched. So let's just understand the setup, right? And hopefully in a minute I'll tell you why the setup is actually useful, right? So if a vertex has high ownership list, I said that it's going to be at level 1, and I also said that a vertex at level 1 is surely matched. This is an invariant that we will maintain. Okay? And if a vertex is free, then this free vertex is going to be at level 0, okay? And all its neighbors are going to be matched because we want to have a maximal match. Yeah, and every vertex at level 0 also owns at most root n edges, less than root n edges, and all the matched edges are at the same level. So now, before I go to the insert, right, so probably we'll just try to write dark on this. So let's assume that, so let's understand the framework. You have a sequence of updates, right? So U1, right, U2, and this is what I'm interested in. So let me, this is, let's say, insert, and then you have a delete, and so on. This is a fixed sequence, right? And this is a fixed sequence of edges that are presented to you by the adversary. So this says delete a particular edge, this says insert an edge, delete an edge, and so on. Now let's look at a vertex, right, which has high ownership list at some point in this algorithm. Right? And now, by these invariants, I should ensure that this vertex goes to level 1. And in level 1, I must ensure that this vertex is matched. Okay? How am I going to choose my partner, or how is this vertex? Let me call this X. Right? X has high ownership, right, which is root n, okay, and it's moving to level 1, and it has to choose its partner. But what we want to ensure is that it should choose a partner, hopefully, so that it remains matched to this partner in spite of all these updates that keep happening for as long as possible. Right? That's the goal. So that way, our advertised analysis, you will have a handle. So if you know that a high ownership vertex gets matched to a random partner, it's most likely going to get matched to the partner which is in the middle rank of this update sequence. Okay? So if you just select the random partner, it just selects one of these guys at random, the update sequence is fixed, right? And then you ask, what is the expected rank of the element that has been chosen as the partner? Okay? That's going to be somewhere in the middle. Now, so let's say that this vertex now chose this guy. In expectation, this is the middle rank vertex, middle rank where in this fixed update sequence that we are hoping to defeat by the usage of randomness. For so many updates, half the updates, this vertex has, the algorithm has to do no work, right? Because it just doesn't have to change the matching. It just needs to do just constant work, right? When these updates, so these are deletes, right? So at this point of time, it owns all these vertices. The only work that can happen at this particular vertex is if these edges are deleted. But this vertex is matched to this edge. This is our good edge. And when these edges are presented, the algorithm just needs to do constant effort to find that these are not in the matching, and therefore they don't affect the maximal matching at all. So it's just a constant thing. Therefore, half the time, right, by a random choice, you can expect. Right? You don't have to do any work. Right? This is where our gain is going to be. Therefore, if you look at this whole update sequence, you're going to see that for a high ownership vertex, before this guy gets deleted, half of these guys are going to get deleted before this, in expectation. Right? So therefore, if your update sequence is of length p, right, then p by the ownership list of x, right, is the amount of effort. Those are the total number of times that you have to do a high amount of effort. When is the high effort? When this edge is basically deleted, you need to find out who to match it to, right? Which might be large because of the high ownership here and so on and so forth. So it's just so many times when you will do an expensive amount of work. So this is the second parameter, which is not immediately visible, but by the usage of randomness, you get this handle. What do you trade it off against? You trade it off against the size of this list, right? Of this ownership list. Right? Observe that if you just thought of this as just a degree, you don't have this handle at all, right? So, and then clearly this root f is the size of the ownership list. Right? So that is the whole intuition behind this algorithm. So what I'm going to show you is the steps in the data structure, right? And the different components of the data structure. Hopefully, I'll be able to convince you that there's a lot of work to be done to fix three-length augmenting paths from here on. But this is the intuition, so let's just go through the other one. Alright, so let's assume that the edge that is being inserted is UV. And let's look at the easy case, right, that U and V are both at level 1. And let's assume that the three invariants that I have mentioned are already being respected, which means both of them are matched. Right? So you have nothing to do basically. You can quickly figure this out and add U and V to one of the ownership lists. You can do this arbitrarily. And therefore you just spend a constant amount of time. An equally easy case, right, which won't be equally easy when you want to eliminate three-length augmenting paths, you can think about it, is when the endpoints of the edge are across the two levels, right? So one is at level 1, the other is at level 0. Right? Again, U is matched. This guy is not going to make life any easier for you because you only want to maintain a maximum matching. So, I mean, it's not going to give you a larger matching, so constant time you can get rid of this step. So this is the more interesting case, right, where U and V both are at level 0, right, and there are many things that can happen. So, but definitely the ownership lists of both the vertices are going to become larger, right, because level 0 an edge is owned by both its endpoints. So one thing that you could do is you could just match the two of them. If both of them are free. Now, after doing that, you check if the ownership list is touched the value root n. It's touched root n. So then U decides to go to level 1 and it removes the edge. Right? Every edge that it was sharing ownership, right? So for every UW, right? So observe that W was in level 0 also, it just takes ownership of it and then it goes to level 1. Okay? I'll come to that in 1. So what happens? So maybe a picture is. So this is level 0 and this is the edge UV. Okay. Now what has happened is that the degree of the ownership list of U has increased to root 10. Okay. And because the ownership list has become larger, U takes the ownership of all the other edges and goes up to level 1. What it does before going up to level 1, I will tell you. So this is W. Both are at level 0, so therefore this edge is owned by both the endpoints. U takes ownership, and then observe that this is a newly added edge, and we have matched U and V, or U was already matched. So now U basically finds a random mate among the owners. So that's because the ownership list has become large. It goes to level 1 and chooses a mate at random. This is hoping that this mate will stay in the matching in the presence of the input sequence, which is static. So this is what happens. It randomly settles itself, okay, by selecting an edge uy from its ownership list. And here basically what it does is that now this y, whatever edges it was owning, okay, y is going to come down to okay, so let's just see this picture. I'm sorry. So U is here. Okay, U selects a random guy, okay, from its ownership list and picks up y. Okay. So this y could have already been matched to someone, okay, and
y goes to level 1, so y is at level 0.
Yeah, sorry, thanks. Yeah, sorry. Yeah. Right, so y is here. Right? So y is at level 0. Remember that u was at level 0. Right? It's owning edges. Right? It's taken the ownership of edges, and y is one of them. Okay? So observe that if y was higher, it would have owned that edge. So now y is at level 0. So it takes ownership of the edge uy, and every other edge that y had owned, right? Y takes ownership of it and y moves up. Right? So basically we add, right? U gets matched to y, and the mate of y is basically removed and uy is added into the matching. But before that, because y has gone up to level 1 to ensure that okay, I think that should have been y, and that caused the problem. I'm sorry. Okay. So the level of u is 1 and level of y is 1. Right? So this is a mistake. This is what caused the problem. Okay. So y goes up, and this step ensures that y owns all the edges that it had to level 0. So this ensures that all our invariants are maintained. Now x has become free. Right? This was the previous weight of y, so that is the random matching of u to y, right, caused the previous mate of y, right, which is x, to now be free, and that's returned in the function call. Right? But let's see how much time this one takes. It just takes order ownership of u, which is basically root 10 at this point of time. And so what do we now do? Let's observe one of the properties. Right? If x is not null, you recall that the ownership list of x is small, which is smaller than root 10, and you just find a mate for x among its ownership list to see if by checking if anyone is free. Right? So probably U is a little over here. I'm sorry for this. Right? So in this case, X is the vertex. You look at every edge that X owns. Right? Now it's X which is free.
So X.
X which is free. Right? And here I just have to check if one of the neighbors of X is, one of the vertices owned by X is free, which is, so this is the vertex X, right? This is U now. U has got matched to Y. Y was matched to X earlier. I have to look at the ownership list of X, check if one of these is free, and this I do exhaustively by enumerating each one of them. Right? Please ignore the U here. The U is actually overloaded. Right? And so let me call this free. And then add the first guy that you find from the list into the match. Of course, there's one more thing that needs to be done. Recall that at the beginning of this process, U, right, whose ownership became large, was matched to V, and the random choice might have left V still single. Right? U made a random choice among its ownership list. Right? U was matched to V because of the insertion. So now this V basically is single, and we fix it by again doing the naive settle, right, at this particular vertex. It doesn't matter, don't look at the name. Okay. So this is okay. So let us just see what we have done. Right? The insertion of an edge caused a vertex of high ownership. Right? And we have kind of conservatively or preemptively sent it up to level 1, ensure that it is matched, and it is matched to a randomly chosen vertex. And the handle that we have is that the input sequence generated by the adversary, right, for half the ownership list, right, we expect that half the elements in this ownership list will be deleted. Right, before this particular edge is being deleted. That gives us a good handle for the amortized answers. That's basically what we have done here. Alright, so deletion probably is. Right, so let's look at the easy case for deletion. Right, so you delete this edge UV, you find that it's not in the matching. Right, that's easy. Right, you just have to update the ownership list appropriately. On the other hand, if it is matched and you have this vertex at level 0, then you just reduce the ownership list of the two of them, and you can do an exhaustive enumeration. Right? And that takes just root n time or less than root n time. Now, the challenge is only when UV is in the matching. Right? Probably a better picture. So this is level 1. So you have UV, right? And this is deleted now. And they have their own ownership lists, OU and OV. At this point in time, we know nothing about how large the ownership lists are. We do know that when they did come up, one of them had a high ownership, right? But we don't know at this point in time what the input sequence has done to the ownership list. Right? So therefore, we have this method which does handle deletion at both the endpoints. So sorry, this was the match edge. Now this is gone. Alright. So the first thing that happens is that, so let's consider this handle deletion function at one of the two endpoints. So which is U in this case. So let's see this, right? So you may own an edge to W, right? But it's kind of become single. W is already matched to somebody else. Let's call this person X, right? Because W is at level 1. Now X is also at level 1 because of the invariance. Okay. If U was owning this edge, what U basically does is it transfers ownership to W. In other words, it takes the edge UW from its ownership list and gives it to W. Because just in case U has to come down, you need to maintain the invariant that W owns the higher level endpoint owns it. Right? So that's basically what you do. So which means you scan the ownership list of U, right? Which could be large, and transfer the ownership to the other point. So transferring this just basically adding the edge to the ownership list. But there are potentially linear number of times that you have to do this. After doing this, if the ownership of this guy is large, so what does that mean? You now owns lots of these edges, right, in its ownership list. Right? So in which case you again do a random settle. Right? You basically, what does a random settle do? Again, by repeating this, I think this will become clearer. You choose one of its random neighbors. Let me call this P, and let Q be its mate. Because we have this property that a vertex and its mate are at the same level, the ownership list of Q is small. We match U to P, set PR, and fix Q deterministically by searching its ownership list, which is small. Right? So therefore, this takes lesser than root n time. This takes lesser than root n probes. However, the difficulty here is that you have to sample one of these guys. Therefore, this takes, right? You can only say that this takes order n time. Otherwise, what happens is that you basically has an ownership list which is smaller than root n. Again, I think there is a small typo here. Okay? So you basically falls down to level 0 first, right? Because its ownership is small. Then it takes the ownership of everybody else that it was not owning earlier. Okay? And then it basically searches for a free neighbor in its neighborhood, in its ownership list, and gets matched to it. Otherwise, it remains free. Okay? As you can see, this is really the most expensive. This delete function is asymptotically the worst case. All that you can bound is just theta of n. You can't do that. So let's just, yeah, so this is a little more bookkeeping. I'll just skip it. If you just think about it, you will get to this step. Right. Alright, so for the insertion, these are the different cases for the worst case update time, right? So which we just analyze. Some of them are just constant time, and then the maximum that happens for the insert is when they are both at level 0, right? In which case it takes order root n, which involves a random settle. And at the end of this, the vertex U will be matched to a randomly selected partner from its ownership list. So the delete is basically very expensive, right? Especially in the case, right? In the case when U and V were matched and at level 1. Now let's just complete the analysis using the framework of Bhubaneswar, right? So we'll see where the challenges for the analysis for removing three-length augmenting paths lie. So let's just look at, so basically the key concept here is to visualize the running, the execution of this algorithm, right? You abstract it out as a sequence of intervals. Each interval is called an epoch. Right? So an epoch is basically a time interval during the execution of the algorithm. Right? And this epoch is associated with an edge E, right? And this edge E is in the matching. Right? This is the time instant at which E enters the matching, and this is the time instant at which E leaves the matching. So therefore, the execution of the algorithm, at every snapshot, you have a set of maximal matchings, right? And the edges essentially, for every edge which is there, you in the matching, it's kind of stretching an interval as time goes on. Right? So this edge is in the matching. In the next time step, if the edge continues to be in the matching, then the epoch associated with the edge becomes one time unit longer. This is basically what one can visualize. Right? So now one needs to set up the correct random variable for calculating the expected running time. So we observe that the only effort is when the matching changes. This is a small, right, but crucial observation. There is significant work done only when the matching changes. Otherwise, all the effort is constant. Okay? And therefore, we measure or we kind of keep track, okay, of the amount of effort that is put at different points of times, right, which are endpoints of some epoch, and set up the sum total running time. Therefore, if you ask me to write the total running time, right, it's basically you have the sum over all the epochs, the time at the beginning of the epoch, plus the processing time spent at the finishing of the epoch. Observe the beginning of the epoch, right, is okay. So E is kind of overloaded here, right? So let me call this P for it. Okay, so P is an epoch. The epoch P is associated with an edge which is in the matching. Right? It can either enter the matching or leave the matching. Now, among these, some of them are low cost lesser than root n, and you can throw them out. For the ones which are expensive, observe that we always create a random variable. Right? So whenever a vertex, right, creates an edge, right, when its ownership list becomes large, then it randomly adds an edge from its ownership list, right? And therefore what we get is P is a sum of appropriate random variables, right? And at the beginning of the epoch, the amount of effort that you put in accounts for the time spent in processing that whole epoch. And now you can use linearity of expectation, and then you can ask for the expected time, right, that is associated with a particular epoch, and that is what we analyze. Right? There are two. The expensive epochs will basically account for total number of updates divided by root n, right? Because it's only every root n steps that an expensive operation is done in expectation, plus, so let me call this T1, plus T2 times root n. And this will essentially give you a total of root n. So you have to multiply this by n. This is just a total, and the worst case time is n. The rest of them are T2 operations which are inexpensive, which just put root n time. So therefore the total expected running time will give you root n. So this is, in a sense, I just set up all the formalism to ensure that I can use linearity of expectation, which I justified earlier. Alright. What are all the things that will not work? Right? Yeah, I'll just give the whole sequence of ideas and measures. So now we want to use the same idea, right, to eliminate tree-line augmenting paths. So let's just see what are all the ways in which tree-line augmenting paths can happen, assuming that we are using the same kind of leveling methodology. Okay, so now, so an edge UV is inserted, right, and it's, sorry, an edge UV is in level 1, it is in the matching. Okay. So now, let me just quickly go through this. Right? So this was in the matching, this edge got inserted at some point of time, right? And now this edge got inserted at some point of time. Now just to figure out that there is a tree-line augmenting path, right? When this edge gets inserted, right, you have to ask, right, sorry, the other way around, when this edge gets inserted, you have to ask, right, okay, so you can figure out that B is free in constant time. Now you have to ask the mate of U, right, the other endpoint, does it have a free neighbor? You can observe that this degree or this ownership could be sufficient, very large, and you need to somehow figure this out efficiently. Right? This is one challenge. Right? So therefore, you need to set up a data structure which can answer this quickly. Right? This is one challenge. And so this is a case where you have a level 1 matched edge. Right? So there is this edge which was already there, and there's this edge which has been inserted. This causes this kind of error. Another one which may not be too hard, but interesting things can still happen, is that you have this edge. So this edge is there. Sorry, Vy is the matched edge, and Uv was already, Yz was already there, and Uv is the inserted edge. Now you need to check if this forms a three-linked augmenting path. This seems to be okay because the degree here is quite low. Deletion gives rise to a whole sequence of so let us just look at this. So once I show the representative one, which is the most interesting one. Right. Answer B. Right. So let us just, so actually it shows up as W here, I'm sorry. So you have UV, right? This is this was a matching edge that is now deleted. That was forming this kind of a force cycle. Now you need to figure out, once this has been deleted, you need to figure out, right, which of these edges could potentially participate in a three-linked augmenting path. You have to search for it, right? You have to find its mate, find the other endpoint, check its mate, and you see if one of them, right, one of its neighbors, right? So that could be W, right? UV could have been the edge which has been deleted. So this is again quite an expensive effort because these edges are owned, right? By the higher level endpoint, so you don't know how large this degree is. So here, it's not just the ownership, but the degree also plays a very important role, right, in the amount of effort just to find whether there is a three-linked augmenting path. So I'll just outline my invariants and then stop. Right? So we have 5 invariants. And, so here are the things that we basically do, like BGS. We ensure that if U is a level 1 vertex, right, so then U is for sure matched, right, so and if U is a free vertex, then U is a level 0 vertex and all its neighbors are matched. So very similar to what we had. And a level 0 vertex has ownership lesser than root n. However, it is quite possible that you may have level 0 vertices, right, whose degree is smaller than root n, whose ownership is more than root n, but they are matched. Right? So therefore, this is one more invariant which is very helpful for us in searching for three-linked augmenting paths when they happen. And the mates are at the same level. Right? And we always ensure that whenever we find a three-linked augmenting path, we fix it. So the first 3 are 1, A, B, and 2 and 2 are exactly as in, and 2 and 4 are exactly as in the previous work. The additional 2 conditions that we enforce, right, on the matching that we maintain is that if a level 0 matched vertex, right, has degree smaller than root n, it can stay at level 0, though its ownership might have crossed root n. And we kill three-linked augmenting paths. Okay, so I think I'm done. Right? So I kind of presented all of Bhaskara, Gupta, and Sen. Right? The first part of it, it's a paper which has a lot more. Right? And the challenge is to argue that these invariants are actually sufficient to maintain